Yes, my name is Stephen McEntee, and I'm going to talk about my own Python module called pflacs. It's a module that's designed to enhance the engineering design process. And if you want to follow the slides online, they're available at that link. Okay, a little bit about me. As was mentioned, I'm a mechanical engineer. I've been working as a subsea pipeline engineer in the oil and gas industry for 20 years, and I've got my own startup, Quilca, that has been developing data management and analytics software for the subsea oil and gas industry. I've been Python programming since 2003. Before that, I did some Perl and Fortran. So there's some contact details here as well. I'll just show you for a moment some of the things I'm working on. This is my startup. This is its main product, Visinon. It's data visualization for subsea data. That's pipeline survey data you can see there, and it's got a data management module as well. But I'm not here to talk about that today. I'm here to talk about these modules, mainly pflacs, but also there's a support module, VM3, which is a Python tree data structure, and I've got another module for carrying out design of oil and gas pipelines. Now, my motivation, as you can see at the top there, is to enhance the engineering design process with Python. And just a definition, when I'm talking about engineering, I'm referring to the traditional physical engineering domains of civil, mechanical, or structural engineering. I realise that term engineering can mean different things to different people, but in the context of this talk, that's what I'm referring to. Okay, just some comments on, give some context. How we talking? I'll just make some remarks about how we use computers in the engineering design process. They're very much coloured by my own experience working for a small consultancy in the oil and gas industry, particularly in the late 1990s and the early 2000s. When I finished in college, I can remember one of my professors saying that I'm an engineer, not a computer programmer. I want to engineer, not spend my time sitting at a computer. And that attitude reflects a lot of what people in engineering would think. Computer programming is not what they want to do. But nonetheless, we have to use them because, like everyone else, computers have taken over our profession. During the 1990s, that professor's vision almost came true with the introduction of Windows 95 and PCs on every work desk. It seemed as if we'd finally come to a stage where we had a sort of an intuitive computer environment that everyone was familiar with nice GUI-driven programs. And it seemed now that we didn't really have to train people to use computers. We could just give them these GUI programs, and they were basically self-explanatory. So it seemed like there would be a good productivity boost from the introduction of all these PCs compared to the old paper-based way we did engineering in the previous generation. So the idea seemed to be that engineers didn't need to program anymore. So my professor I referred to, he'd be happy about that. Let the computer programmers do the programming and the engineers do the engineering. We get the best of both worlds that way. However, sometimes it seems like we didn't get the best of both worlds. We got the worst of both worlds. Engineers didn't know how to write a computer specification, so often the software that they specified was a disappointment. Programmers, I felt, didn't understand how engineers worked. They seemed to think just point and click user interfaces were the way to go, as it was at that time. At that time, when you were using a lot of that software, you had to be sitting in front of it. The personal computer was very personal. There was a constant stream of windows with OK buttons on them that had to be addressed. They didn't seem to do anything except interrupt you. And in a way, I felt that quality and productivity was being affected by this. So just an overview of the engineering design process that my software is intended to address. You start off with a design basis, so you take your input data and all the knowledge you've got about your project, and you distill it into a design basis that defines the parameters and the design codes and the constraints on your design project. The analysis are often organized in a hierarchical structure. Base case at the root and then load cases underneath it, so that it fits very comfortably into a sort of file system hierarchy, and people would often organize their analysis in that way. So you proceed with your analysis. We'd have three levels of analysis. One's basic, simplistic analysis. 3 is advanced analysis. 2 is a sort of in between. And the approach we took was very deterministic sort of analysis. We used conservative assumptions to deal with any uncertainty, and this led to a good deal of over-design, I would say. It certainly wasn't an optimization process. So the process was very iterative. There was a lot of rework. Because of all the assumptions we made in our design basis, we often found ourselves having to rerun work, and that was always a pain. Our toolchain was pretty typical for anyone working in an office now. It'd be office software, spreadsheet, word processor. You'd have a computational spreadsheet as well, most usually MathCAD. That was the favorite, because MathCAD in a way sort of replicated the previous calculation and paper-based approach to carrying out computations. As I mentioned, there's a PC on every desk, but it was quite cumbersome. Engineers were, at that time, mostly, if you actually did a time and motion study on them, what you'd see is that it's mostly data entry that they were engaged in. And we spent an awful lot of time formatting reports. The reports were the deliverables to our clients, and consequently their formatting became quite elaborate, and this made them quite brittle, so that needed an awful lot of attention. I'd say most of our time was spent formatting reports. So in effect, what we'd done, although there was a productivity boost using PCs from a computational point of view, it was still a very manual process, and we had in a way replicated the previous paper-based workflows on our PCs. Now some people noticed this, it wasn't just me. This is a remark in a book on pipeline engineering by Palmer and King, well-known pipeline engineers. And they said the design process needs to be made more efficient, less costly. There's no reason why it couldn't be completely automated, and the reporting could be automated as well. And that was in the book published in 2008. At that time, nobody was interested in doing that because we had a business model based on selling engineering man-hours, so there was no incentive to do things faster. And also, there was a feeling that you needed to have engineers in front of the computers. That was a sort of quality assurance way of automating things broke that sort of quality assurance with hands-on people doing the work. So just to go through this a bit quickly, but I'm just going to review how you might use engineering for computation. I'm going to do a simple calculation pressure of water depth. It's a simple formula, rho GH, rho is the density, G is gravitational acceleration, and H is the water depth. Okay, the simplest way you might do this is just to write a script. And you might say, well, that's completely inflexible. Why would you do it that way? You'd have to have a separate script then that way for each load case. But actually, that's the way we did it. We were using MathCAD mostly. And although MathCAD has batch and automation tools, we didn't use them. We just produced a separate worksheet for each load case. That's just the output from that, so I'll just skip over that. A better way to do it is to have a function. You can do also, function is very flexible. You can use it to put a front end on and use it in a spreadsheet, just call it from your own, bundle it in a library and call it input. So I'll just quickly go through this. I've just run that function, it's done some calculations. An alternative way is to the object-oriented approach. So I've made a class here. Using the same object-oriented approach is very convenient for engineering because we work with objects and they can map very well onto Python objects so that you can give it properties like water depth and density, and then you have a method that you can call on it and do your calculation just like the function. So I'm just import that and set up 2 instances of that ocean class to do my water depth, water pressure computation. And I can call this you just invoke the method on the objects and they get values out, because if the values aren't explicitly specified, then it will look at the object attributes. And that's very convenient, but the disadvantage of that is that you're stuck with the interface I've designed. If you look down here, I've built in G into this, so that if you wanted to change G, you wouldn't be able to do it with this class. So I've made interface decisions that might suit you, that might not suit you. So it's not quite so flexible, this approach. If you wanted to use a different value of G than 9.81, which I thought, well, most people in the world use that value as a standard value for gravitational acceleration. But if you were using, say, US customary units, you'd want to use 32.2 for the gravitational acceleration. You couldn't use this class. And of course, you could go back to the function where you can override the default value and use that. So there's more flexibility. But the point I'm trying to make is there's convenience in objects, but there's more flexibility in functions. So we want to set up a computational framework. So there's some idea what we want to do. We want flexibility. What I would like to do is have a framework that is light touch and unopinionated, so that you can import your functions and retain the flexibility of functions, but also combine that with your objects as well. So what I'm trying to do here is get the best of both worlds. I want the flexibility of pure functions combined with the convenience of objects. And I'd like just a few other things I'd like to be hierarchical, because I pointed out that the way we do our analysis, our load cases, is very often in a hierarchical structure. I'd like to do lots of analysis, so we want it to be scalable. And also automatic reporting would be very nice. Now, I haven't actually achieved all of these aims, but these are the general aims that I'm aiming for. So can we have it both ways, functions and classes? Well, Python is very dynamic, flexible. So let's make a class, and I'll make an object, a pipeline object. This is a 16-inch pipeline with a half-inch wall thickness. And I'm going to do a very simple calculation. This is a hoop stress formula. It's one of the simplest formulas in stress engineering. PD over 2T. P is the internal pressure in the pipe, D is the pipe diameter, and T is the wall thickness. Superior types of engineers, like process engineers and structural engineers that I work with, would often make snarky remarks like pipeline engineering is just PD over 2T. And in a way, they're right. So, how are we going to do this combination? We can going to make a function to do that borrow hoop stress calculation, PD over 2T, that's all it does. And I want to put that into my class, so I'm going to compose it in. So I'm just going to make it as an attribute on that pipeline, on the instance, the pipeline, in that pipeline class. And I'm going to call it on the pipeline instance that I made. When I do that, well, fortunately I put it into a try exception block so that you can call it the exception, but that didn't work, because what I was hoping that would do, I haven't specified any parameters. I was hoping to get those parameters from the object, but that would require magic. There's another interesting point here that it's saying there's two required positional arguments it's looking for, and there are actually three in the function. So evidently that P is becoming the self, the reference, the object instance. So that's a bit of a problem. So a way around that would be to make it into a static method so that there's no self-reference, and call that. So, okay, I can do that, and I can give it the parameters and it works. But the problem is that's no better than that's a static method. It's no better than a plain function. So an alternative way is, maybe what I need to do is capture that reference to the object instance. I call it object here, obj, but that's self. So we want to capture that, and we want to tell our function to look up the object attributes if they're not explicitly specified in the function. So let's try that. We plug that in, and we call that, and that works. We specify the pressure, the other two, it gets the wall thickness and the diameter. It's getting that from the instance attributes. So that's been calculated correctly. So I call that patching in, but some of you might be aware there's another term for this form of programming. It's monkey patching. You're modifying code during runtime. And as you might guess from that term, it's not entirely approved of. But I would say, in this instance, practicality beats purity. We're engineers, so if it works and it's useful, we'll use it. So, how are we going to achieve this with Python? Well, we know that one of Python's superpowers is that it's highly introspective. And in the inspect module, there's a couple of functions that can help us here. There's a signature function that gets function signature. And there's an older function, getArgSpec. When I first started this out, working on this project in 2012, I was using PyCon 2, and I used this getArgSpec. And as a proof of concept, I worked on it, and we got it working. And it seemed like the concept would work. But I dropped the project for a while, and when I came back, I discovered that this inspect.signature was now in the inspect module. When I saw that, I thought, that has been designed for this specific use case. Somebody must have done this already. But it turns out that I was wrong about that. Inspect.signature is actually used by PyDoc for when help is invoked. We'll see that in a minute. And as far as I'm aware, nobody's done anything like this so far. So just to show you what inspect.signature does, we'll import from the standard library statistics module, and we'll take a look at the standard deviation function. And you can see there inspect.signature gives you the call signature for that function. And there's another function I'm using there to look at the source code, so we can see that that's Python code. So as I mentioned, PyDoc uses this when you invoke help. So if you can see there, if you look at you can see the doc signature is given when you invoke help, but you also get the function signature as well. So that's that in action. But according to the documentations for inspect.signature, some callables may not be introspectable, so we'll try something from the standard library math module, square root function. We'll try to inspect that, doesn't work. Try to look at the source code, that doesn't work. Well, we know that actually these functions in the math module are actually wrappers around the C math library. So that's the reason why that's not working. And look at the help string, you can see that it doesn't give you the function signature at the top there. There's 3 dots because inspect.signature doesn't work in this function. But you can see that whoever wrote this function has embedded the signature into the doc string itself. However, I was using Python 3.6 for this, so just for interest I tried Python 3.7. And sure enough, there's been some change in the math module. It now, the inspect.signature does get the signature. And when you look at help, yes, whoever's looking after that module has changed the doc string, and it's now working with PyDoc, giving you that signature. But still, it's still a C function, you can't get the source code for it. Anyway, that's just a digression. Introducing my module pflacs. So this function pflacs, it stands for Fast Road Cases and Parameter Studies, free format, it's not in order. That's the GitHub repository for it. It's a lightweight, unopinionated framework. So what I'm trying to do is use my own functions and other people's functions with my objects. And I want to do it in a lightweight and unopinionated way. In other words, I don't want to have to modify your functions to do this. So, and as I mentioned, I'm using inspect.signature to help me do this. So we import pflacs, we make a base case object. Use this premise class to do that. And we give it a couple of parameters. There's a special parameter class that pflacs uses. And that puts 2 attributes into that instance there, A and B. And this function here, simple function just to test it, adds 3 numbers. So we've got a special function, plugin function, that will plug that function into that base case instance. And what that does is it plugs it into the class. Actually, it becomes a class attribute, that function now. And it's not simply composed in, it's not just a reference to an external object. So we call help, that works, that's good. And I'm just going to invoke that addNums function, and it magically comes up with the number 15 because nothing's been explicitly specified. It's taking the object instance attributes to calculate that. And you can see that base case A plus base case B equals the return value from addNums. And you can also explicitly specify values just like a conventional function, and that works as well. But in this case, we explicitly specify the B parameter, but what the value is, it's a different value in the instance itself. And just a few more examples of running that, but because of time I'm just going to skip down through those. Plug in another function. Now this, I'm going to use another function that does a simple subtraction operation, but in this case, you know, if you generally want to plug in functions into your objects this way, people aren't going to line up their naming scheme with yours generally, so you need some way of mapping the function names onto your naming scheme in the object. So there's an argmap argument that is provided, and it provides a mapping between the function arguments and the object arguments that you're plugging this into. So that just adds in a third parameter C, so you can use that. And there's the value C6.5 at the bottom. And okay, we just invoke that without explicitly specifying any parameters. And just the next line is just to check that it's the return value of that subtract numbers function equals what you would expect from the object attributes. Now, I said I wanted this to be hierarchical, so I've made this into a tree. It inherits from a companion module called vmtree, which is a simple Python tree. And I'm going to make a child node, like I want to set up a load case here. So I can just make another premise object, and I make it a child of my base case. The base case is the root of the tree, and this is its first child. And the way it works is pflacs applies arguments. If you in this order, if you explicitly specify the arguments when you call one of those methods, it'll apply those. Then it looks in the node instance for if the parameter is not supplied explicitly, look in the node instance. And if it can't find it there, it ascends the tree to see if it can find it in an ancestor node. And if it can't find any of those, it will apply any defaults that are specified. So just using that, applying that simple function just to test that it's all working okay, and it is. So I'll just skip through that quickly. There's another class, convenience class, that automatically does the calculations. So it's called calc, and it's a subclass of the premise class. What I do here is I specify, I tell it to use in this case I'm telling it to use the subtract nums function. And what it'll do is, there's a dunder call specified here. It will use invoke. If you invoke this instance directly, it will call that subnums function. We'll just do that. We invoke the instance, the LC1 instance that we just created there directly, and we'll just check that that lines up with the expected value we get from that subnums function. Okay, so that's just another load case, and also we can put our data. There's a convenience function to put our output data and input data into a data frame, a pandas data frame. So we want to make our tree bigger to add on more load cases, so we can clone one branch of the tree and make it into another branch. Of course, it's just a clone, so we'll have to change the attributes so our new load case will do what we want. So here's another function. In this case, again, I need to remap the argument names, but I'm using function annotations. You might have thought function annotations were just for type hints, but actually, no, they can be used for other purposes as well. So, just to move on a bit, invoking that node, get it to calculate a value, and then put the values into a data frame. And this is what our tree has started looking like now. So we're building up a larger number of calculations in load cases. That's just, the tree can be iterated over conveniently in the for loop because it's a generator. And what this is doing is identifying each calculation node, and then it's running each node. So it's very easy to rerun the entire tree of calculations whenever required. So your study can be serialized in a pickle file, which is just recovering the pickle file and creating a new object from that. And also we can, pickle files are very convenient for serializing large tables of data, so we'll use the HDF5 format for that. And we've got a convenience function that will put our pandas tables into the HDF5 format. And this HDF program shows the runs I've just been doing. You can see the tree over on the left-hand side. There's some of the tables I just prepared there from the HDF5 file created. Right, so as I mentioned, I've been using this to automate pipeline design work, and I've created my own module to do some pipeline design calculations. It's not complete yet, so this will be very sketchy. I'll just skip over it. This just basically repeats in more detail what I was saying earlier, where I set up just a function that I want to do calculate pressure containment for a pipeline. This is how we really do it, not using that simple borrowed formula that we saw earlier. This has got 21 arguments, this function. You can see now why I want to use objects, because using this as a pure function is very inconvenient for that number of arguments. So just creating my tree now, creating a couple of premise nodes, and plugging in a function to do some calculations as well. And down at the bottom, what I'm doing is I'm actually creating a second pipeline, so I'm cloning the nodes I've made, and I'll update the parameters, the attributes on those nodes, and I'll iterate over the calculation tree, over the pflacs tree, call all the calc nodes, and print out that tree. So this is a representation of the structure of the tree now, and all the calculations we've been doing. So anyway, I hope that gives you some idea of how it works. I don't want to go into any more detail than that now. Now, one interesting question is, will it work with third-party libraries? And the answer is yes, it will, as long as they're pure Python functions, and that we can get the call signature for them. So here is an example of some Python libraries that have functions in them that I found on GitHub, and we're going to test pflacs, import these libraries and see if it runs. So we need to, just going through this, we're going to set up some cases where we plug in a function from that seawater module that I identified there, the first one. And we set up some parameters for that. And we plug in the density function that we looked at the help string for, and do a calculation on that, and it throws out the value that we're expecting, 1027. That's the seawater typical value for seawater density. Okay, I'll skip down through this because time is getting a little bit short, but this is another pipeline library that I'm doing a pressure calculation in. So it does something similar to the function that I saw earlier, that I showed you earlier. And we plug that in, we do some calculations, and okay. And I'm also plugged in a lot of NumPy functions on pure Python, so they'll work as well. So I'll try out this, do an interpolation on the arrays that I've set up here, and I plug this into my pflacs object. I'm going to invoke it. I'm remapping the parameter names to make it a more convenient sort of for my purposes. I invoke it, and it does that interpolation calculation using the NumPy function has been remapped. Okay, so just to return to that math.square-root function, we saw that inspect.signature will work with it. Will it work with pflacs? So we'll give it a try and try and import it. Unfortunately, no, because if we look at the signature, that / means that the arguments go forward are positional only arguments, and at the moment pflacs applies the object attributes as keyword arguments, so that currently doesn't work. Maybe look at that in the future. So in conclusion, I think I've taken pflacs to point a proof of concept stage. I've shown that you can take pure Python functions and, without modifying them, plug them into objects. The pflacs software is still at alpha stage, so there's still a development being done on it. Future developments, I'd like it to work not just with pure functions, but also with methods as well, and classes too, because a lot of, when I was searching for functions to test pflacs with on GitHub, I found a lot of people prefer to use objects perhaps for the reasons I outlined earlier. So I'd like to be able to use those with pflacs as well, so that's something in the future. I'd like to have automated reporting. Maybe a GUI would be nice. It's just pure Python at the moment. I'm thinking of creating a JupyterLab plugin to do that. And we'd like to be able to scale it. That's something we haven't done yet, but VM3 can be serialized into a Mongo database, so that's one way of doing it. And maybe the tables, maybe we use Postgres for that. So basically what I want to do is, at the moment it's working as a desktop program, but I want to use it on the data center in the cloud with a platform like the physical platform that I showed you at the start. So that's it for now. Thank you very much for listening.